Two galaxies are colliding, and somewhere inside that collision, stars are being born faster than the physics of the collision should allow. When galaxies exist in isolation, star formation follows a predictable rhythm. Gas clouds cool slowly, collapse under gravity, and ignite into stars at a rate constrained by how much molecular gas is available and how quickly it can shed thermal energy. A typical large spiral galaxy converts roughly 1 to a few solar masses of gas into stars each year. The process is self-limiting. Stellar winds and supernova explosions from newly formed stars inject energy back into the surrounding gas, heating it, disrupting it, suppressing further collapse. The system regulates itself over billions of years. Galaxy mergers change the conditions. When two large galaxies begin to interact gravitationally, their gas reservoirs respond. Tidal forces stretch and compress the gas along asymmetric paths. Streams of material fall inward toward the merging nuclei. The gas loses angular momentum and concentrates in the central regions of the system. Compression increases, cooling accelerates, and the rate of star formation rises sharply. This is expected. Models predict it. Observations confirm the general pattern across hundreds of merging systems. What observations do not consistently explain is the scale of the acceleration. In some merging systems, star formation rates climb not by a factor of 2 or 3 above the isolated baseline, but by factors of 10, 50, or more than 100. Certain mergers produce what are classified as ultra-luminous infrared galaxies, systems radiating much of their energy in the infrared because the rate of star formation is so intense that newly formed stars are still embedded in the dust and gas that produced them. The energy output from stellar birth in these systems exceeds what the available gas mass under standard collapse timescales should be capable of generating. Colliding galaxies are creating stars at rates that the known mechanism of gas compression cannot fully account for. Competing explanations exist. Neither has closed the problem. The first set of explanations centers on enhanced gas compression. When the merger cascade drives gas into the central regions of the interacting system, the compression is not uniform. Shocks form at the interfaces where gas streams collide. These shocks are not gentle. Velocity differentials across the shock front can be hundreds of kilometers per second. The gas behind the shock is rapidly compressed to densities far exceeding what would be reached through gradual gravitational infall alone. At these densities, cooling timescales shorten dramatically. The gas becomes unstable to gravitational fragmentation on timescales much shorter than the standard star formation models assume. The result is a burst of fragmentation and collapse that can in principle generate star formation rates far above the isolated baseline. This explanation is consistent with observations in a general sense. High-resolution imaging of nearby starburst mergers shows star-forming clumps concentrated in regions of known gas compression near the nuclear regions or along tidal debris streams where gas streams are converging. The spatial correlation between shock-compressed gas and active star formation is detectable. The problem is quantitative. When the observed star formation rates are matched against the gas densities inferred from the compression models, the efficiency required, the fraction of available gas actually converted into stars per freefall timescale, often exceeds what shock-driven compression alone can explain. Standard collapse models, even with enhanced shock compression, suggest a conversion efficiency that falls below what the luminosity and stellar mass growth of the starburst systems imply. The gas should be partially stabilized by turbulence injected by the very shocks driving the compression. The turbulence should resist collapse as much as it promotes it. The efficiency problem does not go away. The second set of explanations focuses on what might be suppressing the regulatory feedback that would otherwise slow star formation down. In isolated galaxies, the feedback loop between stellar energy output and gas disruption is one of the main controls on how fast stars can form. Supernova inject momentum and thermal energy into the interstellar medium. Radiation pressure from massive stars pushes outward against infalling gas. Together, these mechanisms prevent runaway collapse. During a major merger, the geometry of the system changes in ways that may reduce feedback efficiency. Gas compressed into a thin, dense nuclear disk presents a different structural environment than the extended disk of an isolated spiral galaxy. Supernova remnants expanding into a denser, more confined medium may lose their momentum more quickly through radiative losses. The energy deposited by stellar feedback may not couple as effectively to the bulk gas reservoir. If the feedback loop is partially broken, if the gas does not respond to stellar energy injection as strongly as in the isolated case, the self-regulation fails, and star formation proceeds at a higher rate for a longer time before exhausting the supply. Observational evidence for weakened feedback during starbursts is indirect. What can be measured is the ratio of star formation rate to available gas mass, called the star formation efficiency per unit time. In starburst mergers, this ratio is systematically elevated compared to isolated spirals with similar gas fractions. Whether the elevation reflects stronger compression, weaker feedback, or both is not something current spatial resolution or gas kinematics measurements can separate cleanly. Two mechanisms, both physically plausible, neither capable of accounting for the full observed range of starburst intensities on its own. The problem deepens when the time scale of the burst is examined. Starburst episodes in major mergers are transient. Simulations suggest they last on the order of tens to a few hundreds of millions of years before the gas supply is exhausted or expelled. Yet during that window, the total stellar mass formed can rival what the progenitor galaxies accumulated over billions of years of quiescent evolution. The burst is not just fast, it is disproportionately productive relative to its duration. Reproducing this disproportionate productivity in simulations requires assuming either a higher than observed gas inflow rate into the starburst region or a star formation efficiency that exceeds what can be independently constrained from gas mass measurements. Neither assumption is firmly grounded. The simulations that match the luminosity and stellar mass output of the most extreme starbursts tend to require input parameters, compression factors, feedback coupling efficiencies, that sit at the edge of what is considered physically defensible. No simulation currently reproduces the full distribution of observed starburst intensities from first principles. Beyond the efficiency and feedback arguments, a third possibility sits less comfortably in the literature, that the relationship between gas density and star formation rate used in models, calibrated primarily on isolated and weakly interacting galaxies, does not hold in extreme merger environments. The standard star formation scaling relations are empirically derived. They describe what is observed across a wide range of galaxy types and environments. But whether those relations extend without modification into the conditions of a major nuclear starburst, where densities, pressures, turbulence levels, and radiation fields are all orders of magnitude above the calibration range, is not established. If the underlying scaling relation breaks down in extreme conditions, then the mismatch between predicted and observed star formation rates is not a problem of missing physical mechanisms. It is a problem of applying the wrong framework. Neither the compression explanation, the feedback suppression explanation, nor the scaling relation breakdown explanation is ruled out by current data. All three may contribute. The relative weight of each likely varies between individual mergers, between merger stages, and between spatial regions within the same merging system. The observational data do not yet have the combination of resolution, sensitivity, and physical parameter coverage needed to disentangle them. What measurements exist point in consistent directions without converging on a mechanism. Infrared luminosities confirm extreme star formation rates. Molecular gas masses measured through carbon monoxide emission confirm elevated efficiencies. Resolved kinematic maps of nearby starburst mergers show disordered, turbulent gas flows consistent with strong shocks. None of these measurements isolate a single causal driver. The core observational conflict remains. Star formation is occurring faster than the physical processes thought to govern it should allow, and no single explanation accounts for the full range of what is observed. One layer of the problem is partly resolved. The spatial connection between merger-driven gas compression and elevated star formation is established. Something about the collision concentrates gas in ways that accelerate stellar birth. the direction of the causal chain is not in doubt. What remains unresolved is the mechanism that sets the rate. Why compression in some mergers produces bursts an order of magnitude more intense than compression in others, why the efficiency of gas-to-star conversion during the burst exceeds the range that standard models predict, and whether the regulatory processes that control star formation in quiescent galaxies simply stop functioning during the most extreme merger events, or whether they continue operating but are overwhelmed by conditions that fall outside the domain where the models were ever valid. The collision produces the stars. What determines how many is still not known.